I'm not sure how recently he found this out, but Yo-Yo Ma is in his family tree. I don't know if this is a 23andMe or you met him or how far away he is. Are we talking like second cousins or 30th cousins? I need to know that answer eventually. So please, everyone, welcome Daniel Chen.
Okay, so welcome everyone. Hello, my name is Daniel. I am currently a PhD student at Virginia Tech, studying data science education and pedagogy in the medical, biomedical, and health sciences. And if you want to learn about some of the work that I've been doing, there is a website called ds4biomed.tech, which is a data science book essentially geared towards people working in the biomedical sciences. So it's a work in progress. In the past, I was an intern at RStudio, where I worked on the Grade This package, which is a code grader for LearnR documents. And recently, I've been involved in carpentry since 2014, so I've been an instructor since then. But recently, I am a trainer, so I am someone who can train instructors. And as of the last couple of weeks, I am officially the community maintainer lead. So I help manage all of the 50 plus lessons through the carpentries. And like Jared mentioned, I have a book that is a blatant ripoff of his book, which is called Pandas for Everyone. Today, we're going to talk about tidy evaluation. And there's three main parts: quasi-quotation, quosures, and data masks. And depending on which part of tidy evaluation we want to work with, there's a few topics that we need to cover, like quotation, closures, and environments. So we're going to be using dplyr as an example because it's something we're familiar with. And I know the talk said we're going to talk about dplyr, like all of dplyr, but in reality, we're really just going to be using the dplyr select function. And so the data set that we'll be working with is the famous Palmer Penguins data set. And the first thing we're going to be covering is how do we select columns as a review. So in base R, we can select columns using the regular square bracket method. So we can say row, column, and there's a parameter called drop. If we have a single column, we can put in our column name in string. And then if it's a regular data frame, not a tibble, we have to specify drop equals false. And that's how we get a data frame object back. Otherwise, we get a vector. Tibbles have this, tibbles and data frames. If we need to select multiple columns, we can pass in a little vector of two things, and then we can select multiple columns. Another way we can select columns is using a $sign. So we can use the $sign or a single column with drop equals true, and then we'll get a vector object back. In base R, there is a subset function that sort of behaves very similar to dplyr in the sense that we don't have to put quotations around the columns that we want. We can just use the column names as is. And then the thing that we've all very accustomed to is the dplyr select function that I don't really have to go into more detail about. But one other thing that's really important is another way you can subset columns. It's not really advised when you're doing analytics work, but you can subset columns based off of the actual index position, like the number. And we'll see where that comes into play. So first things first, what is quasi-quotation? And the thing we have to learn is actually what is quoting. So what is an expression? So the R code that you write actually is really composed of two things. It's like the code that you write, you hit enter, R takes that code, runs it, and then gives you an answer. So when we type 3 plus 3, we get 6. But there's a base R function called quote. And if we say quote 3 plus 3, instead of evaluating it, we get back the code 3 plus 3. And so we can save that to a variable, and then there's a base R function called eval, and then that's sort of the premise of lazy evaluation, where we're taking an expression and evaluating it later. So you can think of an expression like the string representation of your code, but it's not really because it's its own object, but it's a pretty reasonable approximation when you're trying to think about this stuff. So where does rlang come into play? Rlang has a function called expr for expression. So we can do the same thing, pass in 3 plus 3, we get 3 plus 3, and then we can evaluate that expression using base R, or in rlang, there's a function called eval underscore tidy, and that'll do the evaluation on that expression through rlang. And so expressions can be different things. They can be a call, a symbol, a constant, or a pairlist. Those are all really just implementation details under the hood. So if I say like 3 plus 3, you'll see that I'll get a language object back. But if I put in 3, then just a number, I'll get a number object. And then if I put in like something, you'll get like a symbol. So you can quote things, but under the hood, it's like stored a little bit differently. And so how do we select column. So like I said before, we can pass in a direct string into a column. So we can pass in species directly, or we can save species into a variable and pass that into our data set directly. But if we pass in species on its own, you'll see that you'll get an error that says species not found, right? And that's because it's not saved to a variable, it's trying to evaluate it and it doesn't exist. So in a tibble, this is sort of just a special thing with tibbles, but you can pass in these quoted name objects in tibbles and it'll work, right? So tibbles have this additional feature that doesn't work with regular plain data frame objects. So if we try to do that in a regular data frame, you'll see that, like, for example, I'm using the iris dataset. If I try the same subset on a data.frame, it doesn't exactly work on a tibble. So these are things that we have to think about. So let's write our first select function on our own. It takes in a data set and then a column. And then all we're doing, just like before, we're saying data using some regular square bracket notation and putting drop equals false, so we always get a data frame back. And this is nothing special, right? We passed in a string column, we get a column back, right? And it works in tibbles if we put in quotes, but like I said, it won't really work if we just pass in species on its own because it's trying to evaluate that, right? But I just showed you how to quote inputs, right? So let's use that quote function that we just learned about, and let's quote the actual column that comes in. But then we find out that no, that doesn't exactly work, because when we wrote quote col, what actually got passed into data is actually col, not species, right? So it actually quoted the thing that we told it to quote, which is exactly what we told the computer to do. So that's a problem. In rlang, there is a function called nexpr, or enriched expression, and you use this function inside of a function to sort of handle that, like, hey, I want you to quote this thing, but don't quote the variable or the function parameter I gave you, actually quote the thing that the user passed in, right? And so there's, we use nexpr for that. So we can use nexpr for our third attempt at this. So instead of using quoting, we're putting nexpr. And then now if we put in species without a quote, it'll do that for us. And we can save this object to another variable and then pass that in along the way. But if we pass this into a data frame object, it doesn't exactly work properly because tibbles have that additional feature that data frames don't have. So the way we handle this more generally is we use the index position. So we take the whatever the user passed in, and then we write some regular R code that essentially says, hey, look through all of the column names in our data set, find the ones that match, and then subset on the index directly. And then we get the same exact features for both sides. We can say pass in species for a tibble, or we can pass in species that's the quote for data frame. We both get the same result. And that's weird thing of like using the index position. If you sort of dig your way and follow the dplyr source code, it pretty much does something like that. You'll see that there's this match call that ends up calling this vec as location. So under the hood, dplyr is doing something very similar. So now we want to expand this. How do we get it to work with multiple variables? Before we showed you a function called nexpr. So if we put an s at the end of it for nexprs, it will be able to capture essentially ... And then what we get back is a list of expressions that was passed in for ... So what I did was we have a list of expressions, convert it to a character, and then do regular R things to get the index position, and then subset that way. And you'll see it works for both a tibble and a data frame. The thing that I noticed when I first wrote through this, I wrote which instead of match. And the difference between that is if I used which, it preserved the same order of the original data frame regardless of what I used in. And if we use match, if we specify the columns in a different order, it'll give you back the data frame in the order you specify. So that's the little difference between there. So what exactly is quasi-quotation, which is essentially quoting, unquoting, and requoting. So before our last attempt, we used nexpr to like handle the weirdness that's going on. We turned it into a character string, and then we did regular R things with it. So variables can be both quoted and unquoted. So we can say like, okay, now we want column as species as the variable, and we want to pass that in as one of the column names for selection. And you can see right now in our current function, we can do that in base R, and we can do the same thing in dplyr using dplyr select, and then we get a little warning that's saying that it's like evaluating a thing, but it's only a warning that's once per session. So we want to be able to mimic that behavior. So we can do that. Our function right now, if we take in penguins and pass in island and year, we can do that. But right now it doesn't exactly work if we pass in call name, right? Because we can send species as a variable to call name, but it's not working properly right now because it's trying to pick up like colname as a column in our data set, and that doesn't exist. And that's sort of the error that we get because we're trying to subset on an NA. So the problem is we need a way to treat a variable as a variable, not as the quoted item. There is a train running across my window, so if you hear rumble, that's what that is. So if we want to unquote, so the thing is we want to actually unquote call name, get the parameter that the user passed in, and then quote it back and use species in our subsetting function. And so that's where you see this bang bang operator, this 2 exclamation marks. And what that does is it actually unquotes the variable that we passed in. So now if we say call name is species, and then we can use pass in bang bang call name, and what that will do is it'll unquote, it'll take call name, turn it into species, and then pass that into our function. So that's what that bang bang operator is doing. So how do you know if a function actually quotes its inputs? So you first try to run the function as is, and then try to run that parameter outside. So if we ran penguins and island, but if we just ran island on its own, you'll see that the first option, it actually runs without error, and the second option, it can't find island. And we've seen this like in our normal day-to-day R programming. If we library rlang, rlang is probably not a variable that you have, and so like library is another function that quotes its inputs. So at the end of the day, this bang bang unquoting is really just selective evaluation on parts of a quoted expression. So it's something that's quoted, but I actually want you to unquote that one little bit because I want to pass in some other user input. And so bang 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 is bang bang for ... right? So that is probably a sentence you didn't know was a sentence until right now, but essentially that is what the triple exclamation mark is for. And so what is bang bang bang? It is how do we pass in or selectively unquote a list of things. And so we can have a bunch of expressions using expers and say species, island, year, and then we get actually a list object back. And then if we pass in that list object to our selection, it doesn't know what to do with that. So then what we say is, hey, take those expressions, sort of unpack it, and then like evaluate that list, right? So evaluate that ... and then we can actually use our selection function to do that. dplyr on its own actually has one more check. So you can sort of have this mixed series of columns. So we can pass in species as a column name and pass in column name there. And then we can also use bang bang column name, and it'll selectively unquote that. So dplyr allows both sections, and our current function doesn't work that way. And the way for us to make our function behave more like dplyr, we have to learn a thing about Quosures, which is a quote and a closure. And so if I say closure, we've probably all seen some error essentially along the lines of object of type closure is not subsettable, and typically the reason is because we are writing in our code something like df bracket 1, and that's because df is actually an R function that's built into the stats library, the built-in stats library. So what we're actually doing when we do this sometimes, if we didn't specify df as a variable, is we're trying to subset a function, and if you try to subset like select from dplyr, that doesn't make sense, and you'll get the same exact error. So what exactly is a closure? A closure is something like a function or an expression plus its environment. So what is an environment? Well, we can create a new environment using the base R function called new.env. And we can say in this environment, create a variable x, assign it to 3. And the thing is, if we, in our regular global environment, just say x, it doesn't exist, right? You'll get an object x not found. And if we try to say like, hey, use that x variable, right? So like 3 plus x, it doesn't exist. But if we say 3 plus x, and then also pass in this environment E that contains the definition of x, it'll work, right? So that's what environments are. And so formulas actually encapsulate an expression and its environment. It's not just for models. And so if you say like tilde 3 plus 3, you actually get the expression 3 plus 3 back. And that's why you see the tilde being used throughout the tidyverse. It's sort of the quick way of quoting something. And so we can actually subset formula objects. Like the first object is always going to be the tilde, and we can get different expression parts out of it. And we can evaluate them. So formulas is a form of an expression plus an environment. And so what we can do is we can take a formula, we can take a separate environment, and then we can run this eval, pass in the formula expression, and then pass in the environment of the formula and have it evaluate the formula expression in a given environment, right? So a quosure, instead of like that formula, is really an expression plus the environment. So it's a different like object, but it's really a subclass of formula without the little tilde bit. And this allows quasi quotation, and so the user might use the tilde, but from the developer's point of view, you'll be working with quosures. And so quosures behave very similar to functions in that there's this part that's the expression, and then there's this other part that is the environment. And then what you can do is run eval tidy on a quosure object, and then it'll say, okay, I know the expression bit, I know the environment bit, I'll run those two bits together. And so quosures in practice, we actually don't use that new quosure function, but that sort of exists in the world of rlang for completeness sake. So the last bit of tidy eval is this concept of a data mask. And so essentially data mask is a data frame or a list that essentially when you try to run code, that's where it starts looking for variables first. So it supersedes the actual environment in terms of variable lookup. So you can also think of it as like this is an environment that goes before the current actual environment where variables to look for. So what we can do is we can create a quosure using new quosure, and then we can pass in a data frame that says y of 1 to 5. And then in eval tidy, we can pass in the quosure expression and a data frame or the data parameter. And so right now our expression is x times y. The quosure itself has the value 100 for x. And when we say run x times y with x equals 100 and pass in a data object of our y values, we'll get the 100, 200, 300, 400, 500. So it's using that data object as a place to look for additional variables. And you can see at the bottom there, if we try to run it on its own without this infrastructure of dealing with environments, we get different, it either doesn't work, or if we want to totally replicate our example, we would simply say 100 times df $y. So that's exactly what that eval tidy function is doing under the hood. So in our previous try, we handled the weirdness, we unquoted the arguments, we found the index positions, and then we did regular R things to return our data set. But it didn't deal with the fact that we passed in call name by itself. And so we used the data mask for that. And so we still handled the same weirdness. And essentially, you can see here, I'm using set name sequence along to get all of the columns of our data frame. And I'm running eval tidy to say like, hey, all of those inputs, evaluate them in this context so I can get the actual column name back. And then, just to handle the fact that sometimes the user might pass in a character string, we dealt with that too. But at the end of the day, select, arrange, tidy select, all of that stuff, all it's doing is getting a vector of index positions back and then returning that back to you using base R, that's penguins, the index, and then drop equals false. So there's a lot of things I didn't cover. For example, there's this colon equals operator that essentially lets you quote things to the left-hand side of an equal sign. I also didn't talk about pronouns like data and .env, so you can read more about those. But the TLDR is if you want the user to pass in a string and the function itself internally uses a string, that's something that we're all used to. So for example, ggplot has an AES string option, and we can use our function as is. If you want the user to pass in a string, but the function takes a quote, what you want to do is convert it to an expression first, and then unquote the expression. So we can use AES with bang bang there. If you want the user to pass in a quote, which is essentially without the quotations marks, so the actual code, and then the function itself takes a string, you capture the expression using nexpr, convert the string to an expression, so there is an rlang as string, and then you can execute that as is. And then if you want the user to pass in a quote and the function itself also takes a quote, you first have to use enquo to capture the quotation and then unquote it. And that's where you see this curly embrace notation in rlang. It's essentially doing that quoting and unquoting for you. And so with that, there is this metaprogramming chapter in Advanced R, and I've probably read that like once a month for the last year. So just keep reading that until you eventually get it is sort of what I ended up doing. So thank you.
Thank you very much, Dan. That's awesome. Stream starting soon. It's awesome. Love Dan's technology as always. He always brings it, both on-screen technology and others. So that was really great. With that, folks.